Bismillahirrahmanirrahim. Welcome students to the online lecture of digital logic design. In the today's lecture, we will be discussing encoders and the decoders. In the last lecture, we discussed combinational circuits of multiplexers and demultiplexers. In this lecture, we will be discussing the encoders and the decoders. Uh, we will be first discussing the decoders. You know that any discrete quantities of information can be represented by binary codes. We have studied a lot of binary codes. A binary code of say n bit is capable of representing up to 2 raised to power n distinct element of coded information. A decoder is a combinational circuit that converts the binary information from the n inputs to a maximum of 2n output lines. So we will see that how this decoder function is works, and we will just also design a circuit diagram for decoders of different configurations. We will be discussing the decoder in a form of an N to M line decoder, where the M should always be less than equal to 2 raised to the power M. N. It means that for any given decoder, we could have the number of output line may be equal to the maximum of 2 raised to power n, but they also could be less than that. Generally, we design a decoder, or we say that it is not like one to many or many to one concept of the mux and demux. It involves certain n to m line inputs, inputs and m outputs. Binary code of n bits can be represented in the form of 2n distinct coded information. Only one for the decoders, only one one output could be a high, or say have a value of 1 at any given midterm combination. First, for input, what we do is we form a truth table like this one. In this truth table, we are representing basically a 3 to 8 line decoder. It means it has a say block diagram like this one. It has 3 input lines. We write it as 3 to 8 line decoder, while it has 8 outputs from D0 to D7. The inputs are selected in this way, that if we have say 3 inputs X, Y and Z, then each of them are represented in a form of 8 combinations, which are represented here as this. Against any combination, only one of the output is equal to 1 and the rest of the outputs are equal to 0. If you see here that for the first combination, which is giving us the first main term, only the D0 value is equal to 1, rest are 0. While for the main term M1, which forms the next combination, only D1 terms is 1, while rest of them are equal to 0. So this in this way, the whole truth table of the decoder is formed, that for any given midterm, only the subscript that is representing that midterm equivalent output is equal to 1, while rest of them are all equal to the 0. So we can see that for all of these combination and the output, only one value is equal to 1, while rest are equal to 0. This also gives us you can say a binary to an octal conversion system, because for any given midterm we have only representing the output that it should be equal to 1. Because you see that for the 000, we would be only be representing that D naught is equal to 1 here, means that first number of the octal number system. Similarly, if you see the last one, it would be representing the 7 for a binary equivalent system. It would be representing, it means that the 7th number, the last number of the octal number system should be have here. So its only value is equal to 1, while rest are equal to 0. And for the same circuit, the 3 to 8 line decoder, which we have discussed, if we just draw its circuit diagram, it's quite simple. That we actually have to generate 8 different minterms. Because we have seen that decoder is similar to generating the number of minterms from the input combinations. So if we have a 3 input system X, Y, Z, we could easily generate the minterms here. We have already discussed this kind of circuit when we studied the sum of product forms and the product of sum form, but we actually didn't name it decoder at that time. But it is quite similar to the same function, because if you see that we are representing here the outputs in the form of AND gate, and each AND gate is connected to X any of the X, Y, Z in complemented or the uncomplemented form. So this output is generated in the form of the minterms. This is representing the D naught is representing basically the M0 or the first minterm, and this is representing the M1 minterm, the second minterm, and similarly up to the last minterm. So these are actually representing all the minterms here, and we are getting from the decoder, we are getting or against the different combinations of input, what we are getting at the output is the minterm value. So for any, if we want to represent any given Boolean function, we can easily represent that using decoder, because we have developed a circuit in which we can generate the minterms like this one, and then we can just connect the OR gate at the output to perform any given Boolean function. We will discuss the case of a simple full adder, because we have discussed this a lot. The sum and carry products are represented in the form of these combination of minterms. The sum is represented in the form of minterms 1, 2, 4, and 7. Sum of product is 1, 2, 4, 7, while the carry is represented in sum of product form of 3, 5, 6, 7 minterm. So if we want to represent them in the form of a circuit diagram, and we have a decoder IC, because generally this decoder comes in the form of an IC combination. So we are using an IC configuration which has 3 inputs X, Y, and Z, while it is generating 8 different minterms from M0 to M7. What we need to do to represent any given Boolean function, we need to just connect an OR gate at the output to have the output. So in this case, because we are representing the full adder, we will just combine all these inputs that are producing one for the sum. For the sum, we have seen that we are getting the one at minterm 1, 2, 4, and 7. So if we just simply combine them in for OR gate, then that would give us the sum here. And similarly for the carry, because carry is represented by minterm 3, 5, 6, and 7. So if we OR all these term 3, 5, 6, and 7, then that would give us the carry result. So in this way, if we have a decoder IC, then that we can utilize it to generate the minterms. And what we need to do is after generating the minterms, we simply need to add the an OR gate to represent it in the sum of product form to represent any given Boolean function. In this example, we have just represented two terms in the full adder, which are the sum and the carry, but we can represent all the 3-bit functions that we have studied so far using this configuration. Now we will be discussing the enable input. We have already discussed the function of the enable input in our previous lecture. And now what we are doing is we will be adding an enable input, and in addition to that, we would be representing the circuit of the decoder in terms of NAND gate representation. With the last slide, you have seen that we represented the decoder using the AND gate term. Now we will be representing the decoder using the NAND gate terms, and we are using here again the active low enable here, which means that if E is equal to 0, then our system will perform its functionality. And when enable value is equal to say 1, and then in that case all the values would be equal to 1, while when we enable is equal to 0, then depending upon the combination of A and B, we will be having 0 at the respective output. because this is represented in a form of a NAND gate representation. In this case, when we have active low enable, then against the any combination of A and B, either of the input from D0 to D3 would have a value of equal to 0, and the rest of the value would be equal to 1. So you can see that for the combination of A and B equal to 0, we would only have D0 here equal to 0, while all other values are equal to 1. Similarly, 1 we have a 0 1 combination, then we have D1 equal to 0. Similarly, for 1 0 we have D2 equal to 0, and for the last one we have 1 1, we have actually it's 0 here, we would have 0 here. So this would be representing the truth table for the decoder with enable input. And what we have done is not just we have added the enable input, but we have also converted this system into a NAND gate representation. And the NAND gate representation, the output of the selection line will be represented by a 0 instead of a 1, and the remaining bits would be equal to 1. Now we will be discussing a little bit relationship between the decoder and the demultiplexer. A decoder with an enable input can function as a demultiplexer. If you look at both the diagrams, then you would realize that both or all can perform almost the same kind of function. This is the decoder and this is the demultiplexer. For the decoder, we have it two input here, and against that we are producing four outputs, D0, D1, D2 and D3 here. We have an enable pin here. So this is a basically 2 to 4 line decoder with an enable input. And for this system, what we do is for any combination of A and B, a single value of the output is equal to 1 or 0, depending upon our implementation of as a NAND gate or a AND gate. Then this would be give us a value of 1, and the rest would be equal to 0. Similarly, for the next combination, this would be equal to 1 and the rest would be equal to 0. And if we look at the demultiplexer, which we discussed in the last lecture, then in the demultiplexer, if we consider the enable pin as an input to the system, and while we have a 2-bit selection line for a 4 output system, then it will perform the same function as this one, because A and B will act as an input, and enable will enable pin at the input will act as a normal enable which is given in this circuit. So behavior of both of these will be the same, because in this we would be changing the A and B as input here, while in the demultiplexer we will be changing the A and B, or the selecting the min terms through this select line. Both will have the same functionality to that at any given time only one of them would have a value of equal to 1. Now we will be discussing a few other circuits relating to the decoders. We could form a decoder, a larger decoder, by combining two smaller decoders. Say we have two decoders, 3 to 8 line decoders. We will be using the enable pin to make it or convert it into a 4 to 16 line decoder. So what we do is we have a 3 input system here, X, Y, Z. We have connected both of these decoder to these 3 lines, X, Y, and Z. So what we have here is that for any given value of X and X, Y, Z, we will be having the same code generated here from D0 to D7, and similar code will be generated here to D8 to D15. What we do here is we add an enable pin here into the both of these blocks, and for adding the enable pin, what we do is that the complemented form of it is goes to the upper decoder, while the uncomplemented form goes to the lower decoder. When W is equal to 0, one value of W is equal to 0, in this case the top encoder decoder is enabled, while this one is disabled at that time. So when it will be disabled, it will be producing the value which would be equal to all zeros, and this would be producing from the range of, you can say, from 0 0 0 to 0 1 1 1, because w is equal to 0 here, and rest would be changing from 0 0 0 to 0 1 1 1. So this would be producing different outputs for d0 to d7. Similarly, if we have a w is equal to 1 here, then in that case we would have 0 here, so this would become disabled, while this will become enable. And in that case we would have these input combinations would be equal to 1 0 0 to 1 1 1 1. Now the last bit would be equal to 1, which is representing the w here, and so for this combination of input we will be getting the output. So in this way, if we combine 2 3 to 8 lines decoder, we will be forming a 4 to 16 line decoders. Now we will be discussing the encoders. Encoders are basically the inverse of the decoders. For the encoders, only we have one input that could be activated at any given time. So if you see this truth table, it is just the opposite of the one which we discussed for the decoders. Now from D0 to D7 are basically our inputs, and the outputs are represented as the 3-bit input x y z. These were actually the inputs and the decoder system. Now they are the output. So this is just the inverse function of the decoder. But there's a limitation here, is that that for any given sequence of the inputs, only one input could be high at a time. Say if you from the first combination, if you see here, that only d0 is high, for the next one d1, for the d2. So you can see that for all these combination, only one input can be active at that time. Say if we have two inputs that are active simultaneously, then the output produces an undefined combination. Say for example, when we have this d3 equal to 1, and suppose d6 also becomes equal to 1, and then in that case what would happen is that we would get a combination in which this we would have 1 1 1 here at the output. Because of this function, we will be achieving all the ones here. But if you see the table, that 1 1 1 could only be achieved when only d7 equal to 1. So it means that neither d3 neither d6 is actually representing this combination. So we have to make sure that whenever the encoder circuit is implemented, we need to make sure that there is not two inputs that are equal to 1. Only at a time, only one input should be equal to 1. And there is one other ambiguity, is that if you look at this truth table, for this truth table, only when d0 is equal to 1, then we have all outputs equal to 0. And also if we consider here that for this case, input case, if all the inputs are equal to 0, I mean from d0 to d7 all are equal to 0, then in that case we would also have an output equal to zeros. So basically two things are represented here, that there are two combinations, that if either d1 is equal to 1, then we would be getting all output equal to 0, or if all the inputs are equal to 0, then we would also be getting again the output equal to 0. So we have to solve these two issues so that our encoder circuit could work properly. For the rest of the circuit, what we do is that for the XYZ term we defined in the last truth table, if you identify the terms in which we have a value of equal to 1, if we just go back a little, this X, Y, and Z terms here, if you just identify the number of times the ones are here, we now it is ones are here, for these are for the Y's, and then this is for the the Z1. So we can from this table what we can do is we can write the expressions of the x, y, and z in terms of d inputs as like this one. The each term is represented here. The d, y, and z are represented here as this one. We can easily represent them in a form of a simple OR gate operation because d0 is not utilized here in any of the terms, so we have not used it. For the rest of things, we get to just for the x, we just combine d4, d5, d6, and 7. It would give us the x, while for the y, we have to combine d2, d3, d6, and d7 here, which would give us a y. And for the z, we would be combining d1, d3, d5, and d7. So in this way, we design a circuit for a simple encoder system. That these are the generally the inputs of the system. At any given time, only one of the value could be equal to 1, and by just ORing these if, with the respective numbers of input from here, we could have a value of x, y, z accordingly. We discussed two issues with the encoder. One was that different combinations of the input were giving the same values at the output. When we have all equal inputs equal to 0, then we were getting the output equal to 0. And when we had d0 is equal to 1 and rest of the inputs equal to 0, then again we were also getting the same output as both of the x and y were were having 0 values. So to resolve this issue, what we do is we add another bit. We call it a valid output indicator. We represent it as a V. The value of V is equal to 0 when all the inputs are equal to 0. And when the value of V is equal to 1 when any one of the input is equal to 1 or more than one input have value of equal to 1. So in that case, V would be equal to 1. So a value of V equal to 0 would be indicating that the all inputs are equal to 0. In this case, we would have an don't care condition at the output. It means that we would not consider this thing at the output whether it's 1 or 0. For the rest of the values, when we have any one of the values equal to 1, we had a problem that if more than one input gets a value of equal to 1, then we had problem at the output. So in that case, what we do is that we have to define some priority for each of the input. So we use the subscript here to define the priority level. We say that D3 has the highest priority, while the D0 has the lowest priority here. So whenever we have a value here, say for the first case here, when D0 equal to 1, in this case we will be having the outputs as the first combination of 0 0 here. For the next when we have d1 is equal to 1, in that case, because 1 is greater than 0, then in that case we would not be considering the value of d0. Either it's 1 or it's 0, it is irrelevant to us. So we will be giving only the priority of d1, and we would be assigning the outputs as 0 1. While if we have both d2 equal to 1, then in that case we will be representing all the inputs of lower subscript as 1 and 0 as x here. So regardless of their values of we would be giving the output as 1 0. And similarly for the last case, we have a d3 here equal to 1. So in this case we would, regardless of the values of the d3 d2 d1 and d0, we would be assigning 1 1 to the output. You can see here that the total number of combination that a 4 input system must form is should be 16 combination, but we are only representing the 5 of them here. The remaining are represented by this term here. Say if we are representing this here x01 0 0, so actually it is representing two different minterms. One is 1 0 0 and other is 1 1 0 0. So it means that x could be both 0 and 1. So we can take so this one term is actually representing further two different minterms here. Similarly, in this case, there are two x values here or dot k term here. So these will be representing four different minterms, and it will be representing 8 different minterms here. Now, if we try to draw a circuit diagram for the outputs X and Y, first what we need to do is we need to design a K map for the circuit. So first we draw the K map for the X here and the Y here. Sorry, this would be also be equal to 1 here. For the initial case, when both of them are equal to 0, then we would have a don't care term here. For the rest of the all the combinations, we just use the method we just defined, that for any given x we could consider both of the values x and 1 and 0 and form all the minterms. So if we solve them through that method, we get all the ones which are mentioned here, and you can clearly see that we could form two different adjacent squares of 8 8 each, this one and this one. So the x could be represented as D2 or D3. Similarly, for the y1 we use the similar method. In this method we would have a one larger square of 8 adjacent ones, and then we could also form a combination of 4 adjacent one here, so that it would be represented by this term. So now we need to represent or draw a circuit diagram for this x and y. These are quite simple expressions. We can easily drive the circuit like this. We have also derived the circuit for the validity bit v here as same as here. So v is also representing, here is actually over here. So V is represented here as this one, because from the table we can see that the value of V is 1 1 for each of the combination here except the 0 0. So except when all the inputs are 0, this value of V would always be equal to 1, and we have just implemented these two from here. So this is the final circuit diagram of this priority encoder. We would be discussing an other concept here, which is known as the three-state gates. Generally, we have considered only the two-state gates so far. It means that the output could be either 0 or 1. The output 0 means that our signal is connected to, say, ground, and the 1 means that it is connected to the VCC or the plus 5 volt. Generally, this is not the case in most of the circuit, as sometimes we also have another signal which is say you can call an open circuit. In the open circuit, our signal is neither connected to the ground nor to the VCC, and it behaves very differently as an open circuit. The behavior of an open circuit or the level at that open circuit is generally known as the high impedance. We also represent it as the Z. Now we will be discussing a few things about the three-state gates. We have initially discussed a buffer gate. A buffer gate is just a simple gate with just have an output value b is equal to a. So this is only stores the value, and the b is equal to a at the output. What we do for the buffer gate is that we introduce an extra signal or control signal into it. We have introduced here a control input here, which is represented as the C. When we have C equal to 1, then in that case the output Y would be equal to A, and the system will behave as a normal operation. When C is equal to 0, then we would have a high impedance state at the output. So when Y is equal to the high impedance state, it means that it values neither representing 0 nor it is representing 1. It is behaving just like an open circuit. So by using this concept, we can represent different functions that we have studied so far in the form of three-state gates. First, what we do is we represent a simple 2 to 1 line multiplexer that we have discussed in the last lecture, and we would be representing that circuit in the form of a three-state gate. So we have used two three-state gates here, and we have two inputs A and B. the select line of the both or the control line of the both of the gate is connected to a single line, which is the select line. Generally, what we do is, depending upon the value of select, A or B is connected to the output. This state gate will behave in the same way, because say when we have select is equal to 0, then in that case we would be having 1 here. So in that case, y would be equal to A, because we would be having a high impedance state here at this gate. Similarly, when we have select equal to 1, then in that case we would be having y is equal to B, and because we would be having a high impedance state here. So in this way, this is procedure is similar to the 2 to 1 line multiplexer. We can also use this phenomena to represent it in a form of a 4 to 1 line multiplexer too. In a 4 to 1 line multiplexer, we have two select lines. What we do is, based depending upon the values of the select lines, our input is connected to the output. For the say first combination, I0 is connected to the output. For the second combination, I1 is connected to the output. Then the third one, and for the last combination, I3 is connected to the output. If we represent these outputs in a form of these three state gates, we are using four gates here. All these four gates are connected to the certain system, so that when their value is equal to 1, only then they are enabled to have a certain output instead of the a high impedance state. So whenever the control input of all these three state gates are equal to 1, then only then they would be connected to the input. Otherwise we would have a high impedance state at the output. Because in this procedure we can only have a single gate that could be activated at a time, so we need to design a mechanism in which only one of these four gates is activated at a time. So to design this mechanism, what we do is we use a 2 to 4 line decoder. The two selection lines of the main mux that we generally use are connected to the inputs of this decoder. And for the two input system, we could have 2 power n, means 4 different outputs, and against any given combination of the inputs we would have 4 different outputs. So for the first combination, we would have only one output equal to 1, while other will be equal to 0. For the second combination, the second output would be equal to 1 and the rest would be equal to 0, and similarly for the second and the third one. So in this manner, what we do is we generate a function that from which only one of these four gates would be activated at a time, because there are the control input of all these gates are connected from the output of this decoder. So this decoder will select only one at a time. So in this way, depending upon the values of S0 and S naught, S1 and S naught, we would be selecting one of the inputs that we want to have only connected to the output, and the decoder will generate a sequence accordingly, and only one of that input would be selected because of this three state gate, and the rest would have a high impedance at the output. So they would be connected. Say if we have choose say 1 0, we have S1 is equal to 1, we set here as 1, and we set it is as a 0. So in this case, basically this output would be selected. So what will happen in this case is that the control value of this would be equal to 1, while this one, and this one would be equal to 0. So in this case, the y is equal to I. So in this way, the whole system behaves like just like a 4 to 1 line multiplexer. Kindly do read these pages for better understanding.